Right, let's start building a physical model to determine the magnitude of the greenhouse effect. We will begin by answering the question, what would be the temperature of the Earth's surface if there was no atmosphere? This repeats the calculation of Fourier. The simplest method to determine the temperature of the Earth in the absence of an atmosphere is to assume that the Earth emits radiation characteristic of a black body of temperature T sub E. But what do we mean though when we say the Earth is a black body? The Earth is clearly not black. Referring to an object as a black body is a technical description. It means the object absorbs all radiation and, assuming the object is in thermal equilibrium, emits a spectrum of radiation determined by its temperature alone. This definition is unimportant, but it will allow us to use certain equations. We could also apply the same characteristic to the Sun. Instead, we will simplify our model by stating that the energy from the Sun reaching the top of the atmosphere, the solar constant, which is given the symbol S, is 1,370 watts per square metre. That is the energy per square metre arriving every second. In creating this physical model in which we will assume the energy impacting the Earth's surface is equal to that being emitted, we need to be careful about the areas involved in absorption and emission. If we take the radius of the Earth to be r, the Earth absorbs solar radiation over an area of pi r squared, that is the cross-sectional area facing the Sun, but emits radiation over its entire surface, that is the area of 4 pi r squared. Okay, we have defined the terms necessary to complete the calculation. What is the energy impacting the Earth every second? Well, it will be the solar constant times the cross-sectional area of the Earth, that is 1,370 times pi r squared. This energy must be balanced by the energy being emitted by the Earth. So if we assume the Earth is behaving as a black body, then the energy emitted per area is given by the Stefan-Boltzmann law. That is, the energy per unit area, also known as the intensity, is equal to the Stefan-Boltzmann constant sigma times the fourth power of the temperature. Note that the Stefan-Boltzmann constant is equal to 5.67 times 10 to the minus 8 watts per square metre per Kelvin to the fourth power. So, if we equate these terms, then the energy into the Earth system per second is equal to 1,370 times pi r squared. And this is equal to the energy out per second, which is equal to the Stefan-Boltzmann constant sigma times the temperature of the Earth to the fourth power times 4 pi r squared. If we rearrange this expression, then T sub e to the fourth power is equal to 1,370 times pi r squared all over 5.67 times 10 to the minus 8 times 4 pi r squared. The pi r squared cancels, which leaves us to solve for the temperature. Initially, we find that the fourth power of the temperature is approximately 6.04 times 10 to the 9. If we take the fourth root, we can find the temperature. The fourth root can be calculated on most calculators, but it can also be calculated by taking the square root twice. Ultimately, this results in a calculation of the Earth's surface temperature of 279 Kelvin. Well, that doesn't seem too bad. In degrees Celsius, 279 Kelvin is 6 degrees. A bit chilly, but livable. But wait a moment, that's not the temperature that Fourier calculated, and you're right. We have made an approximation that we need to correct for. We said that the Earth behaves as a black body. This assumes that all the solar radiation incident on the Earth's surface is absorbed. In fact, some 30% of the incoming solar radiation will be reflected either by the Earth's surface, clouds, or indeed the atmosphere itself. Only the remaining fraction of 70% is absorbed and acts to heat the Earth. The fraction of incoming solar radiation that is reflected is often referred to as the Earth's albedo and is denoted by the symbol A. We can easily include this information about the Earth's albedo to calculate a new temperature for the Earth's surface in the absence of an atmosphere. We simply need to multiply the solar constant by the albedo. When we do this, we find that the temperature of the Earth's surface is 255 Kelvin. This is equivalent to minus 18 degrees Celsius, the same temperature calculated by Fourier. As noted earlier, this would make the Earth an uninhabitable environment. The planet would be a snowball. It should be noted that if we were to attempt to measure the Earth's average temperature from space, this value of minus 18 degrees Celsius is the temperature that would be measured. It is often referred to as the planet's effective temperature. Thanks for listening.